A very good morning. Well, this talk is about optimizing object-oriented programs. Uh, well, there are various ways of optimizing object-oriented programs. I'll cover a few of them or few aspects of optimizing object-oriented programs in this talk. Right. So let's begin with the question: who cares about O languages? We learned about several functional languages and so on. We have non-O languages as well, but of course O programs are written in any language. I mean, they can be written in almost all of the programming languages out there. Even if I work with a language that not purely O, nowadays they provide us ways to write O-like programs. So some content of my talk, even though it would be shown in the context of an O language like Java, some of the content would be applicable even across other languages. Okay, so if you see the language share popularity index based on January 2024 statistics, you would find that most of the programming languages out there in the top 10 most used programming languages list are indeed object oriented. Python, Java, object oriented, JavaScript kind of object oriented, C++ object oriented, C sharp. So all of these languages are in fact object oriented languages, and as I said, even in others many times we write object oriented programs, right? Now object oriented programming provides us various good things, right? So just for the students in the audience, you would learn about various interesting keywords associated with object oriented languages. You would say, oh, all languages have classes and objects, and they together allow you to abstract out one layer of data. They allow you to combine data into groups. You don't need to talk about, let's say, the x and y coordinates of a point by declaring two integer variables. You can club them inside something called as points. So you have an abstraction layer over there. You encapsulate them inside classes. You can inherit, you can basically derive properties from one class and create new classes. Inheritance can also be used to create runtime polymorphism and so on. So you have heard, most of you would have heard of these phrases associated with O programming languages. If you are working with an O programming language like Java, another keyword that comes in is garbage collection. So there are so many good things about O programming languages as we are taught, but then there are several costs associated with object-oriented programs, particularly the costs associated with executing object-oriented programs, right? So let's take an example of Java. In Java, we access fields through objects. So as I said, you need not declare x and y as variables. You can combine them and say, oh, this is actually a point object. But now, in order to get access the x or the y field of a point object, you will have an indirection, right? So there are field indirections created because of this abstraction layer, which is a cost, right? Of course, since you create objects, you also need to store some metadata about objects. In Java, for example, you would store bits in the header of an object that are required for garbage collection, that are required for taking synchronization on an object, and that are required to just maintain the object's identity. A reference is there, and so on. So there are additional stuff there is additional stuff in the memory that you need to do apart from just storing those x and y fields that you intended to encapsulate, right? We said inheritance allows us runtime polymorphism, which is typically implemented by overloading methods. Method overloading again requires you to resolve virtual calls. There is a particular logic we use for resolving virtual calls that also is a cost. Instead of calling functions directly, we can't jump to a function address. We know we have to really find out which function are we referring to. Okay, I did not realize, well, these are gray. Oh, these are not grayed out texts. These are not supposed to be read much anyway, so don't worry about them. It's gray. Yeah. No, it is gray. So they are just to tell you that these are keywords we talked about from previous slides we are referring to over here. So they're not really important. Forget about them. If I have a class animal and I derive a class monkey out of it, I can store monkey objects into animal references, but not vice versa. So we will have to perform some of these type checks before performing invalid operations. We insert we check some of the typecasts rather, whether they are valid, whether we should throw a class cast exception or exit, or is the typecast or is the memory that we are trying to access as if it belongs to a monkey, let's say, is it right? So there is some overhead associated with that as well. Then we said garbage collection is good, but collecting garbage requires a lot of runtime analysis. How do you think about it? Garbage is an object that's not used in future, and we are not burdening the programmer with writing free instructions, let's say. It's a liberation if you don't ask the if you ask me, it's a liberation once you know you don't have to worry about freeing up memory as a programmer. But then how do you collect garbage? You will have to find out where is the object used. Are there references to it? We use there are multiple ways of performing garbage collection. Some of them require reachability tracing in the heap at runtime. Some of them require liveness analysis. All of that is expensive, isn't it? And it's happening at runtime. So the point here is object-oriented programming languages have very nice properties. They ease out the life of a programmer. They allow us to depict the real world in a very concise manner, but they have lots of costs associated with them. Field access is costly, adding to memory footprint is costly, method overloading, type safety, garbage collection. There are more. I have not listed things which are not very relevant to this talk, but it comes with a lot of overheads. And as compiler designers, you know that it's our job finally to remove these overheads. We do it well. That's why OO programs indeed run fast enough. OO programs, not like 1990s where OO programs were just used to represent meta concepts and so on initially. OO programs are in fact used to write system software nowadays. OO languages dominate the software industry in general, as we have seen earlier, but OO code is written for everything ranging from satellites to handheld devices. People are even writing virtual machines or runtime environments in languages like Java now. I am aware of an effort where people are writing a kernel because OO languages indeed provide lots of good things, as we have seen. But OO programs have to be fast enough in order to be usable in all these applications, right? So what all brings performance to OO programs? This is what we would discuss. A wise man once said to me, it's worth learning how the food we eat is cooked. We all consume object-oriented programs, we all write object-oriented programs. And as compiler folks, compiler enthusiasts in this room, we all know about various compiler optimizations too. Now, the point of today's talk would be to add a list of optimizations to your repository of optimizations that are specific to OO programs. That's what we would be doing today. My objective would not be to just tell about work that my group has done or I have done. We have just been in this space for 10 years or so. There is a lot of work that has been done in the last 2 or 3 decades that makes OO programs performant, and my objective would be to give you a walkthrough of some of the interesting OO optimizations. Of course, we would point out related work, recent work, and possibility of future work in the area. Okay, so that's what we are doing today. Now, the contents of this course are derived from the contents of this talk are derived from a course I taught in the previous semester at IIT Bombay. It was called Code Optimization for Object-Oriented Languages. That's why the cool with triple O. And these were the contents, right? So we talked about how do we store memory in object-oriented programs, various versions of pointer analysis specifically suited for object-oriented programs, then optimizations involving allocation, field access, deallocation, method dispatch. We also looked in particular in the context of JIT compilers, just-in-time compilers, where you can perform speculative optimizations based on runtime profile and so on. So all this was there in the course. Today's talk focuses on this third bullet, optimizations involving allocation, field access, and deallocation. So of course there is more. As I told, we'll just cover the surface in this category today. Okay, so let's understand how are objects allocated, how are fields accessed, and how deallocation is done in Java, and then we'll look at some of these optimizations. I hope you'll find it interesting that many of these optimizations are not really so straightforward. There are catches and so on, like we have with non-OO standard optimizations in a typical compiler as well, right? So objects allocated using new in Java are stored on the heap, and the only way to allocate objects in Java is using a new statement. Okay, that's very simple. Java's memory model is very simple. There are stack variables, but any memory you allocate using new goes on the heap. No confusion between where to allocate memory, stack or the heap. By default, everything is on the heap, right? Now, if you have a statement like this, x is equal to new array list of some type t, this gets translated, you know, Java code gets translated to platform independent bytecode, which is then executed on a JVM. The bytecode corresponding to this statement looks like this. You basically allocate memory for an object of the class java.util.arraylist. Then you initialize the object by calling its constructor, and then you store the reference. You got some memory, you initialize the contents of that memory. Now you got a reference back which you stored into the variable x on the left hand side. So that's what this a store. There could be a number here that represents which variable it is on the current stack frame. Let's say it's the first variable on my stack frame, and hence you see an _1 here. Let me tell you, I really find it very interesting. In the beginning, there were very few people in the hall. Now, looking at the crowd, let me first thank you in the beginning itself for being there on a Sunday morning. I will try to show you enough code so that you don't get bored. Okay. All right. So this is the bytecode corresponding to this Java new statement, and you can use something like Java Object Layout Tool, JOL, to figure out the memory structure, how much memory will be allocated for an array list object. If you do it, you will see something like this. It will say, oh, apart from 3 fields that seem to be there in the array list class, there is a field called as mod count, there is a field to maintain the size of the array list, but array list is essentially an abstraction over an array. So you also have an reference to an array called as element data, an object type array with reference element data. So your payload, if you see, is 4 plus 4 plus 4, 12 bytes for storing 2 fields and 1 reference. And then you have these 8 plus 4, 12 more bytes for storing the extra header information that we talked about. You would store the pointer to the vtable to be able to support method overloading. You store information about, you would store some information, let me not go into detail, that would be useful for GC, for synchronization and so on. That itself is 12 bytes in the beginning. So the size of an array list object in this case would be 24 bytes. Okay, this is how it's allocated. Now, how do we access fields of an array list object? Each field access requires a memory load. Well, that memory load may incur a page fault if the page is not there on the memory. It may incur a cache miss if the block is not there in the cache and so on. But each field access in general requires a memory load, and field accesses are often wrapped inside getter calls. That's the right way of writing programs, O programs, right? You encapsulate fields and access them using getter calls. As I said, resident fields may load objects from different parts of the heap, which may not necessarily be resident in the same cache block. So if I had this code, my class T had a field y of type integer, and then some more interesting code. X was storing a reference to an array list object, as we saw on the previous slide. And then let's say after that, I want to get the kth, some kth element of that array list. The kth element would be of type T. I want to access the field y of this class T and do some operation with it. Okay, let's say this is a load. Pardon me for my poorly drawn example. I thought if I just draw it, it would be easier for you to understand. I drew it at the last moment. But X is essentially pointing to an object, as we saw, that 24 byte object that we saw on the previous slide. Now, in that object, there is a pointer to the vtable from which we can resolve which get method are we going to invoke. Internally, get also calls an lm data method, which gives me finally an access to this lm data array. Now, the lm data array is itself an object in the memory. It may not be in the same locality as this original X object. Inside that array, I'm indexing the kth element, which I'm trying to, and then I'm trying to get the field y of the kth element, which is a T object from the memory, right? So this is what will happen roughly. This is what will happen. There are 3 objects in the memory, one array list, and then one T-type object, and I'm trying to get a field of the T-type object. You see, it's not really cheap. There are 3 memory loads involved here. There are 2 method calls involved here. Methods may get inlined, of course, but there is cost associated with all of this. Just think, it would have been so nice if these were just variables on the stack frame. I could access them with constant offsets to stack pointer. Those offsets can be generated by the compiler. So even a simple field access in an O program is costly. That's the claim here. And even method calls are costly, as I told. All right. The third part was garbage collection. So now let's say I want to, there are no free statements in my programming language. So as the runtime who is running the program, let's say I want to figure out when can I free up memory. Say we have allocated two objects, let me give them names. Let me call this object, or the abstract object representing all objects that will be allocated from this allocation site, as O1. Let me call the second object as O2. The references are stored into the variable A and the field F of the object O1, which is pointed to by A. I call a method foo, and then I do some assignment. I reassign A dot F to some other object. Let's assume it's not O2, right? Can we now collect one of these objects is the question over here. In order for me to be able to decide whether I can collect any of these objects, I have to look at various properties of the heap graph at runtime, right? If any of these objects is not reachable from any reference anymore, then yes. If nobody can access that object, there is no reference left to that object, of course I can collect it. Even if it is reachable from a reference I mean, let's say A dot B, A dot B dot C, anything like that. If an object is reachable from a reference, but that reference is not live, what do we mean by it? It's not used in future. So again, I can collect the object. Oh, it's reachable, but it's not live. Knowing all this requires maintaining reachability at runtime, maintaining and determining reachability at runtime, starting from live references. And since you have a call to foo here, of course we have method calls, function calls all over the program. If you have a method call in between, it also requires inter-procedural analysis, because foo may create newer references to O1 or O2, objects reachable from A. I need to find out whether those references exist and whether they are live, and so on. So even if I just want to collect these two objects from a 4-line code over here, I have to perform several iterative data flow analysis as well as inter-procedural analysis along with all its scalability challenges, and all of that is required for garbage collection. So even if you do a conservative version of this garbage collection, which the VMs do at runtime, it is expensive. Okay? That's the point again here. Of course, many Java virtual machines and other runtimes have concurrent garbage collectors, so that they don't really have to pause your program for a long time and do this reachability check and so on while running your program. So even concurrent GCs, the claim is they snatch resources from the program. They are, you create a thread which would snatch resources from your program if your program, let's say, requires that compute power, right? So GC is as well expensive. Lesser the work, which means if such an expensive thing has to happen at runtime in parallel with or along with our program's execution, lesser the work the GC has to do, the better. Okay. All right. So can we, as the compiler, reduce the number of objects? Let's try to answer that question first. Okay, the programmer is happy. The programmer creates classes, allocates objects, has field accesses, method calls, everything wrapped around nicely, and so on. But as the compiler, can we just get rid of some of these objects? They will make us much happier. So that's the first question which we could ask. So essentially what we want to do is, well, there are objects in my program. Can I replace an object by its constituent fields? Can I just decompose the object, okay, and use the local variable, use the fields inside those objects as local variables? Don't worry about any of the overheads associated with objects, right? So let's say I have a class T with two fields, which I initialize to 10 and 20 respectively in the constructor, and later I try to create an object and then access the fields of that object, do some more operations with it. Can we replace this code by something like this? I just declare two integer variables, initialize them with whatever value was being initialized for the fields in the constructor, and then use those variables wherever I was using those fields. So this optimization is called scalar replacement. Can I replace an object by scalar variables? And as you see, if it can be done, it's very good. We just get rid of not only object allocations, we can now access the fields, or rather constituents, with constant offsets from the stack pointer. Most likely these variables will be inside the current stack frame, which means if the stack frame is small enough resident in the cache, I don't have to go and have indirections for accessing the fields. I may incur fewer memory loads, fewer cache misses. And of course, there is no garbage collection needed for the T object anymore, isn't it? So this is called scalar replacement, and this is a very impactful optimization if it can be done. The question that begs an answer is, can it always be done? Can we just remove all the objects altogether? I'm sure some of you saw in the previous slide itself, we cannot, an example of a function call and so on. It's not really trivial. So some people proposed, when can they scalar replace an object? This is one of the people who wrote it very nicely and cited here. So the question is, well, objects are not needed just for encapsulating the fields inside them. What if we actually needed the object to exist in entirety as an individual object, right? Let's say I had code like this, and I had passed the allocated object inside a method foo. Now that method foo's signature would expect a t-type object. I can't trivially pass integer fields to that method. I will have to change code, right? There may be calls to foo elsewhere. If this is a method call with some receiver, I don't know which foo it may be. So I can't really replace trivially all the calls which expect objects with scalar variables passed instead of the object references, right? We can have something like this. If I have a statement, if x equals y, where x and y are two object references of some type, in order to perform this comparison, I again need those objects references. What should I compare? Is it okay to compare the fields if I remove the object and then just decompose it? Not really. What if somebody else could modify the object fields? Let's say there is a static field called global here. They are like global variables in Java. What if I allocate an object and then make it reachable from a global variable? In this case, again, now somebody else might be modifying the fields in a, let's say, parallel thread who can access this, which can access this shared global variable. Then again, I cannot really trivially just go ahead and destroy the object and use its fields as local variables. So scalar replacement is good whenever it can be done, but there are several scenarios, and they seem to be common code patterns that we write, where scalar replacement cannot really be done, right? Object decomposition cannot be done if you need the object in any form. So, well, this is one. Now, people ask interesting questions. So let's look at the following question. Well, it's not trivial to scalar replace an object always, but can I replace an object with a scalar in some paths in my program? Okay, this is the question that was asked by these folks in 2014. Now the point here is, many objects cannot be scalarized only in cold code blocks. What do I mean by cold blocks? In JIT compilers and basically runtimes where you have profile information, you could determine by counting stuff, by counting paths and by counting method calls, you can find out, oh, an object is passed to a method, but let's say only inside an if condition that is executed very few times, right? If the object cannot be decomposed only in a path that's executed very few times, can I do something better? That's the question over here, and the answer is yes. These people said yes, we can scalarize this object in the beginning and rematerialize or recreate the object only if it escapes or only if it is required in a cold block like this, right? So let's say I ideally decompose the object with the two fields over here, and when I see a call to foo, I recreate that object, I rematerialize that object, pass the initial values 10 and 20 of those fields, and that object is expected by foo. I just pass the reference to that object is expected by foo. I pass it along over here. Local field accesses, let's say, continue. So can I decompose an object in some paths? And of course you can see this is again not easy. If we can, then it's good, but rematerialization, let's say I modified the values of these fields in between. It's not like I decomposed x with into two fields over here, so I can just use 10 and 20 whenever I create a new object. I cannot just copy these here. The fields may be modified in between, so this requires maintaining a runtime map from scalarized objects to the values of their fields. Okay. Of course, this object may have aliases, so I need to make sure those aliases also are safe to be replaced by decomposed and so on, but let's not, that's a problem in general. So these people proposed something called as partial scalar replacement, where they could replace objects partially, not for their entire run, but in some parts of the program. If these paths are cold, they are not executed very frequently, then we are still getting benefits of object decomposition or scalar replacement over here. All right. Okay, so this is one interesting thing that's done by many VMs. Now, another question that we could ask is, can we scalar replace an object temporarily? Okay, what do we mean by temporarily? If the object has not been passed around, let's say, to another method, or it has become reachable from a global variable, it hasn't escaped my current scope, then I can scalarize or privatize its fields locally where they are accessed frequently. This is very similar to the previous question, but slightly in a different context. Let's say I have a loop where I access the fields of an object. I read from it, I assign to it, I do some operations with the values that I had stored in the fields of that object. And then later, I am making that object reachable from a global variable. So until this point, no thread in parallel could be accessing this object, and hence that part is taken care of. I don't need to worry about somebody else modifying this object. Let us say there is no alias to this object either at this point. So I can just look at this code locally, and I could transform the object in a way that I scalar replace it in the beginning. Let's say I store the field into a variable, into a scalar variable. I privatize the field, it's called, and I could replace the excesses of x dot f. This is in some way, if you think about it, it's working like common sub expression elimination, and then we can get the result back into the field f of that object before it really is reachable from somebody else. Okay. So this optimization is called field privatization. It gets rid of objects inside loops, which is good because inside a loop I may be accessing memory again and again. And we also proposed recently a smarter cousin of this optimization, which works not only for loops, and it's also a bit more general. I'm not going to talk about it here, but it's very close, where we say, can we just split the scalarization of an object in different parts of a program based on some analysis that we perform a priori. Okay. Now, well, we said if an object can be replaced with scalars, very, very good. Maybe we can replace it with a scalar in some points or in some paths of the program. But there are cases where you actually need information stored in the header of the object. You can't really destruct the object. You need its information at various places. Or let's say you find, oh, it's not just one loop where the object is local, and hence what do I do? So the next interesting question we should ask is, can we allocate objects on the stack itself? Much of the cost associated with object allocation, deallocation, field access was coming because objects can be spread out in the heap anywhere, right? So the next question is, can we allocate the object? We need the object, but can we keep it on the stack frame instead of on the heap, transparently from the programmer, right? So the idea is, we can allocate an object on the stack frame of its allocating method instead of on the heap, which means if typically a reference is stored on the stack and it points to an object in the heap, I could instead store the object itself on the stack frame and make the reference point to that object. This is what I'm talking about here. And this is again a very useful O optimization. This is called stack allocation. Can I determine which objects can be allocated on the stack and do so? Okay. Object components, note that they are still allocated contiguously. So field F1 will still be here, field F2 will still be here, there will be a header still at the top of the object. So, but we can still access those fields at constant offsets from the stack pointer. If they fit in the stack frame, then we have better cache. If the stack frame fits in the in a cache block, let's say, we have better cache locality, and of course free garbage collection. Why free? Because as soon as a method's execution is over, the stack frame will get popped off. All the objects that were allocated, similar to local variables that were placed on the stack frame, those objects can also be just freed away as soon as we finish the execution of that method. Very good. So when can we not allocate, or rather, when can we allocate and not allocate objects on the stack? Stack allocation is again a very powerful optimization performed by various compilers for object-oriented languages. So the idea is, if an object's lifetime is less than the lifetime of its allocating method, then I can keep it on the stack frame of that method, right? So if an object outlives the allocating method, then I cannot allocate it on the stack frame of that method. Let's see a fairly complex example of it. If I have a method foo here where I am allocating 3 objects, O4, O5 and O6. I am passing X, which is pointing to O4, to the method bar. And in bar, let's say I assign the field f, the object pointed to by the field f of the parameter, to a global variable g. G is a static field, so let's say it's like a global variable. This is the program now. Now if you see, O4 and O5 are not accessible beyond the lifetime of foo. O4 is here, O5 is here, and O5 is not passed anywhere here. O4 is passed to bar, but then bar's execution finishes before foo's execution, and O4.f, which is O6, is actually being accessed by the global variable G here, not O4 itself. So ideally, O4 and O5 can be allocated on the stack frame of foo. O6, as I said, O6, and if there are any other objects reachable from O6, they really escape the scope of foo. They can outlive the lifetime of foo, and hence they cannot be allocated on the stack frame of O6 of foo. But again, determining this requires performing points to analysis, a proper points to analysis that, let's say, interprocedural, and then checking reachability, which objects, if O6 is an object that is reachable from a global variable, then the fields of O6, the fields and fields of those objects and so on, all the objects reachable from O6 also cannot be allocated on the stack frame of foo. They may also outlive the lifetime of foo. Okay. So stack allocation is usually done based on these reachability checks over the results of a points to analysis. This whole scheme is usually called escape analysis, and the title of the talk started with "I can capture you." The aim of escape analysis is to capture or try and find which objects can be captured inside a given method. Okay. And it's known to be, escape analysis is known to be one of the most impactful pointer analysis or pointer analysis variations for OO programs. Okay? You should know about it. So as I said, it tries to classify the abstract objects in a program into, let's say, 3 states. If I am performing scalar replacement, if scalar replacement is not possible, I am performing stack allocation, and if none of them are possible, I have to allocate the object on the heap. I could map all the objects into one of these 3 states. Let's say if an object does not escape, then I can replace the object with a scalar. If an object escapes a method, it's, let's say, passed out to a method which does not make it outlive the scope of the allocating method, the lifetime of the allocating method, then I can stack allocate the object on the stack frame of the allocating method. Otherwise, let's say it is globally reachable and hence it needs to remain on the heap. Okay. So typically escape analysis is done using one of these, by mapping the objects to one of these states, and as I said, it's a very powerful program analysis. In managed runtimes though, escape analysis is performed by non-managed runtimes as well. There are versions for C++, for example, but in managed runtimes, for example, JVM, .NET, JavaScript V8, and so on, it's performed typically by their JIT compilers. Now, I'll just give a brief, I'll just have a brief intro of JIT compilers. So the interesting thing about JIT compilers is they can optimize your program while it is already under execution. They can optimize it by not only performing program analysis, but also by looking at some runtime information, values of variables, frequencies of certain paths in the program, and so on. Now, if you notice now, since these JITs do program optimization when the program is already under execution, they are resource constrained. I can't really spend 1 hour JIT compiling a program. Let's say I can't really spend 5 minutes JIT compiling a program that has to execute for 4 minutes. Okay, so JIT compilers have much more constraints on the resources they can consume because they are in place while the program is already under execution, and hence typically, if an analysis like escape analysis that requires points to information, reachability, interprocedural nature, if I want to really perform any interesting optimization, then JITs would have to make some sacrifices, right? So most of the JIT compilers would not attempt at performing interprocedural analysis, for example. Most of the JITs or many of the analysis that are performed by JIT compilers are not even iterative data flow analysis. They are just linear pass, whatever you can compute, okay, go ahead, optimize if you can, right? So JIT compilers really are resource constrained and they make sacrifices on the precision of program analysis. For example, I would not like to JIT compile every method in my program. I would like to JIT compile only the so-called hot methods in my program. How do I determine if a method is hot? Let me keep a counter simply. If a method is executed more number of times than a set threshold, I could decide to JIT compile that method. And only when I JIT compile that method will I attempt even an imprecise program analysis that I intended to do. Okay. Certainly no budget for interprocedural analysis. Of course, you could some benefits of interprocedural analysis come because you can inline methods based on speculation and so on, very interesting stuff, but not always. Right? For example, few of the popular Java virtual machines such as OpenJ9 from IBM and Hotspot from Oracle, they can stack allocate O5 in our previous example only at hot plus levels of compilation. Like we have optimization levels in GCC, there are optimization levels in JITs as well, and they would attempt to perform more complex analysis like the ones we saw only at hotter levels of optimization or higher levels of optimization. Okay. And the object O4 can be determined to be stack allocatable only when I am able to peek inside bar or inline bar, then only I can find out that, oh, nothing happens to O4 in a way that it makes it non-stack allocatable, right? So static analysis, on the other hand, we have a community, we have enough work done in last 50 years in the static analysis community, which can be used to optimize such programs and do ahead of time analysis and really make things interesting, right? What we realized was the reason people don't attempt static, there are multiple reasons. One of the reasons people don't attempt static analysis, or rather whenever they attempt it as well, it seems to be very imprecise, is because in languages like Java, you may not have access to all the code at the same time. You can't really perform whole program analysis. You have, let's say, calls made to libraries, the Java class libraries that, oh, we started very late, no? Okay, it's okay. If the audience is fine, I'll just take 10 minutes. Is that fine instead of 5? Sure. All right. So let's say I pass in objects to libraries and I don't have the code of libraries. So I can't really determine whether the object is made to escape inside the library. So static analysis, even if performed ahead of time over programs like Java, where the whole program is not available for analysis, again seem to be very imprecise, is what we realized. And hence we developed a framework in 2019 called as the precise yet efficient framework, and we perform precise escape analysis in the framework, where we said, oh, you can analyze Java applications separately compared to Java libraries, perform them, analyze libraries where their code is available, analyze applications or other parts of the program where their code is available. But we proposed an interesting way of merging the results of application as libraries, such that you don't really, you can still get the effects of whole program analysis. Okay, so I'll not go deep into this work, but the idea was analyze them separately. Remember, whenever something is passed from one module to another, let's say, or one part of the program to an unavailable part of the program, and then remember and resolve those dependencies among the different parts of a program in the VM. In the VM, don't attempt to perform a whole program analysis, which is beyond imaginable, but just merge these results, do a marriage of the results of applications and libraries, which seems to be much cheaper compared to performing the analysis in the first place inside the VM, while performing JIT compilation without affecting it the cost much over here, of course, right? So, well, this was interesting. This is one of the results that we obtained, and from 2019, there are various groups which have attempted to perform this kind of an analysis. Oh, perform static analysis, but don't make it, prevent it from becoming imprecise, where it doesn't know parts of the program, and then improve the results inside a JIT compiler, which is faster than actually performing the analysis in a JIT compiler, right? So now the next question is, okay, yeah, we'll finish on time, don't worry. So stack allocation cannot be done for many objects as well. Can we do something even more? The point is, if an object is often accessed through a field of a container, let's say, is a class that holds references to other objects as part of its fields, right? So if an object is accessed often from the field of a container, then that object can be allocated inside the container. Let us say I have an object here of a class transaction info, which has two references to two objects, credit account and debit account of type account details. Each of them has their own header and so on. If I inline an object inside its container, the memory structure looks like this. I would have removed the header associated with these account details objects and directly put the fields of account details inside the container or inside the transaction info object. This optimization is called object inlining, This is again a very interesting optimization. And as you can see, it reduces memory footprint. These headers are gone. It reduces field indirections. It can improve cache locality if all of this fits into a cache block and so on. All right. So there is another optimization that we do, which is called object inlining. And again, the same question, when can we not inline an object? So the idea is, if an object is inlined inside a container, but somebody can still refer to that object and mutate the contents of that object, then I was wrong in copying the fields and allocating them inside the container, right? So, and again, like other optimizations, we can't really perform this optimization always. And if I could find out that, let's say, the object is not accessed by any mutable reference, I could safely inline that object inside its container, right? So Java is coming up with a new feature. They have released a preview now. It's called immutable value types, where you would be able to declare a class as immutable. Once you declare a class as immutable, all its objects become immutable, which means those objects can now be safely allocated inside their containers. So this is again a useful optimization which we are working on. We are also trying to answer, if we can inline objects inside containers, should we always inline those objects inside containers? So that's a question we are trying to answer in my group right now, where we say, let's say I inlined this account object inside the transaction info object, but now what if that object escapes? See, escape analysis comes back here. What if that object escapes? What it would mean is, again, I'll have to rematerialize that object along with the fields over here and pass that object to foo. The object needs to exist in its entirety. And if this happens more frequently than the access of the object through its container fields, then I would not benefit anything. Right? I would overcome the benefits that I obtained by putting the object inside the container if I have to recreate the object and keep sending it again and again outside. So we are working on a scheme that tries to balance these effects and tells which objects can be inlined or should be inlined inside their containers. There are more things. Let's not study this, but let's say I cannot inline an object inside their container. Can I still co-locate the object with the container? I would not be able to remove the header of that object, but I would still be able to bring it closer to its references. Right? So this is an object called object co-location, another related optimization that's done by popular Java runtimes. Okay. And yes, if you found that scalarization, field privatization, stack allocation, object inlining, these seem and doing them whenever possible, not doing them every time when possible, if all of this is interesting enough, we are working on several more interesting ideas related to this. We say, can we aggressively allocate objects on stack based on a static precise escape analysis? Let's say I just decide that every object which is passed to a library can be allocated on the stack. Let's say I assume library writers are very benign. They know about escape analysis. They don't really make anything they take from the application escapes. What if I assume this and allocate all objects on the stack? Sometimes I may be wrong. Can I repair things now? Can I move the object back to the heap now? This is a question we are trying to answer, and you will hear it in one of the talks from 12:10 to 12:30 today. So yeah, more to come in the afternoon. There is in fact, there is more work on these lines which will be discussed in the afternoon. And we as a group are working on even more interesting questions related to this space. Can we allocate objects on caller stack when the object cannot be allocated on the callee stack? Let's say I return an object from myself. Now the object cannot be allocated on my stack frame where I am a method, but it's captured in the caller. I could have allocated it in the caller stack and got a reference to that object from there. That's something we are working on again. Can we refactor programs to enable more scalar replacement and more object inlining? We saw scenarios where you need the object. There are interesting ways of transforming programs such that we can remove those scenarios and still write a semantically equivalent program. And we are working on some of the people have worked on, and we are also working on interesting transformations, source-to-source transformations over there. Can we improve partially computed static analysis results with, as I told you, JITs are intelligent in terms of being able to use profile information? Can we improve static analysis based on profile information? or the speculation that's made at runtimes? Can we optimize across language boundaries in polyglot programs? Can we use static analysis to improve JIT decisions? Again, similar to the third question, in dynamically typed languages such as R and JavaScript. These are all the questions we are working on, and I'll just end my talk by pointing out that we have some initial work on many of these, and then we have the remaining group. All of these people are present here. They are working on one or the other questions that we have discussed in the previous slides, and you should look forward to more interaction with them if you find this interesting. Together with me, we form the compilers and programming languages group at CSE IITB, and CSE IITB has many more PL people sitting here in the audience. So you feel free to interact with all of us, and if you are interested in this kind of stuff, please do reach out. Thank you.
How does these optimizations interact with debugging a program? So, for example, you initially brought up the X and Y. I forgot the exact terminology you used. So, when you convert the source code to the opcodes, right? At that time, you are doing the optimization in the compiler. And now, when I run it through the debugger, at that time, what would happen?
So, interestingly, there is a process called as de-optimization that most JVMs use in presence of JIT optimizations, and de-optimization is done on demand. Also, I mean, it's done in other contexts, but one of the use cases of de-optimization is to undo the optimizations that the JIT did based on, let's say, some of the assumptions made at runtime, undo the effects, and allow a debugger to actually inspect the original state of the program. So their de-optimization is already used for already used by JITs whenever they speculate. De-optimization, the same infrastructure, is also used by debuggers in order to debug a program, in order to debug an optimized program.
Thanks for the great talk. So I have two questions. One is, have you looked at C++? Especially some of these optimizations are also suitable for C++. But my question is how it is applicable in the presence of exception handling. Because we always find a lot of exception code, and there is something called observable behavior, right? So they always say that if you change something, the observable behavior where you want to throw exception changes. So what is your thought about it? How it is applicable, these optimization applicable to C++ in the presence of exception handling?
I would need a particular example to answer this in detail, but exception handlers can still go as usual, right? Only, so it's related to the previous question in a way that exception handling will get affected only if I did something which I cannot guarantee to be correct, right? If I change the program and I did it based on some assumptions, let's say learned through the profiles, that could change the program in a way that's not always true for all the executions of the program, right? In that case, we already have a de-optimization infrastructure. Whenever we propose a speculative optimization, we need to propose a fallback mechanism in form of a de-optimization infrastructure associated with that.
Yeah, so and then the second one is this object inlining seems interesting. Especially we have final class, right, where the class cannot be derived further. So yes. Can it be applicable there?
Yes, it's indeed applicable to final classes, and the way Java has defined, or Java designers are defining immutable value classes, is very much derived from the definition of final classes. There are some more constraints on top of that, but if a class is final, it can't even be inherited, which means at runtime you can't remake a reference of that class, point to an object whose structure you are not aware of while compiling the program containing that reference, and hence object inlining can be performed there. So they are very much related.
Thank you.
Yeah, thanks Manas, for a nice talk. A couple of questions. One is again on object inlining. If the objects are big, have you considered looking at the cache effects, benefits, or drops as a result of that?
Yes, indeed. So if the objects are big, we don't really want to inline them. We have an interesting heuristic there where we say if the object size is more than the size of 2 cache blocks, or rather, if the object size is less than the size of 2 cache blocks, and there is some more to that formula, in that case we say, oh, you would never incur more cost than if you had not inlined the object. Otherwise, don't inline the object. So typically, we don't inline large arrays, for example.
Okay. So there, once again, based on my talk yesterday, I think it would be good to look at learned models for some of those things. to see whether you can train certain sets to learn about which objects to inline or not inline?
Actually, we did try that, and we found that there were 2 points to it. We did try it. There were two enthusiastic BTechs who said, I said, no, I'm not interested in machine learning. They said, no, we'll still try it. I said, go ahead. After spending 6 to 8 months on it, no, maybe almost a year. So they did come with some models. The challenge was, of course, no inputs available.
Okay.
Nobody can use those models inside a JIT compiler anyway. It was just an exploratory work. And they found that, what we are trying to, so they were trying to feed the logic that we already knew into the training of the ML model, and we found that, we can already do something which is better. So we have that work in progress that I showed you. It does pretty much determine very accurately on the current state of the art what works and what doesn't.
So how do garbage collectors avoid evicting cache lines that maybe the program wants to use? Like if I'm relying on data locality for my computation.
No, garbage collectors usually try to play safe. They won't really collect any object if it can be accessed in future.
No, but they are accessing certain objects while doing their computation. So they might
okay.
evict the cache for.
Yes. So actually, I could answer it in more detail. There are garbage collectors that take care of this by dividing the heap into generations, so that each younger generation is small enough not to affect the cache locality significantly, and they go and perform a longer collection over a larger portion of the heap only very periodically. So typically you divide the heap into several regions, and you operate once at a time only on a small region. You do the heavy lifting only if the smaller, the lighter collection efforts are not paying off. Right?
Thanks.
But yeah, we could. There is more to it. We can talk about it.
So yeah, meanwhile, I have one question. So when you do object inlining, you are pretty much converting shallow copy into deep copy if this is ever copied. So maybe can you comment on the trade-off?
Yes. So we would create. So there are two versions of it. One is you don't inline all the objects until the last extent. So you don't really go and do it until. There is another version that says yes, do it, but then you would limit the number of, if let's say the object is too deep, you again don't go and inline that object. And most often what happens is, if the object is too deep, already the container size will grow so much that you would get it would fail our size heuristic in the first place.
How do we apply these optimizations in case of application caches? See, a lot of applications use, say, reference objects, what they call reference objects. They load them and keep referring, in applications, actual Java application. Can some of them, these techniques can be lifted to those cases?
No, I don't understand. How is that different? I didn't get something maybe.
I mean, typically application caches are created using containers. And, for example, a lot of parameter classes in applications. They are loaded once, but always read.
Yes. So?
I mean, can some of these optimizations?
Yes, of course. In fact, people are trying to now. So now, from the last 5 years, the Pandora's box has really opened. People are trying to perform optimizations beforehand and load the results of, let's say, store the results of the optimizations on the disk. It's called, let's say, Graal VM, native image in context of Graal. Then load things at the runtime. So you can actually keep things aside and then load them and use them. It doesn't interfere with this as much with some of the infrastructure people have developed recently. Yeah, interesting.
Okay, so let's thank Dr. Manas once again for a fantastic talk.